Welcome everybody to the third lecture in the How to Build and Train Your AI Program. Today, we are going to be going through an architecture called the Convolutional Neural Network, or CNN, as well as some of its more complex advancements. To do this, we're going to be going through several slide decks from the MIT Introduction to Deep Learning course, as well as a lab also adopted from the course, so we can gain a basic understanding of how to implement our own convolutional neural network in code. Let's start with an introduction to computer vision as well as the convolutional neural network architecture. At its most basic level, computer vision is simply allowing a computer to have the ability to see, and most simply, seeing is knowing what is where by looking. Now, in a more complex level, if we look at an image, which we will be doing with our computer vision models, we will be able to identify specific parts of the image as well as what they are. So for example, for this yellow taxi, we can tell where it is in our environment as well as the specific location and what it is as a taxi, as well as other elements of the environment such as the van, people, the stoplights, things in the background, etc. Furthermore, we should be able to identify specific movements so that way we can see where objects are going to go as well as where they may have previously been. Now we understand what computer vision is. We can look at a more complex example. And in computer vision, we have many different examples for applications. In robotics, we allow robots to see the world around them as well as work in their environments. In phones, mobile computing, the photo software that you use for iPhone, the camera application, uses computer vision in order to identify faces in a specific image, which is the yellow box that you sometimes see. And in other applications, there is in biology for identifying specific types of cancers, autonomous driving with auto-driving cars that sense the environment around them, and accessibility for detecting what may be in images, what images contain, what videos contain, and etc. So we are going to actually be using computer vision in one of the later labs in this course for the task of facial detection. So we will take our input images, we will identify the basic features in them with a neural network, and we will be able to identify if it is a face or if it is not a face. Additionally, some other applications like medicine and biology, where we can take images of different scans, for example, breast cancer, skin cancer, or COVID, we can take the images of these scans and use a neural network in order to diagnose if it is skin cancer, if it is breast cancer, if it is a disease or not. Finally, in accessibility, we can use computer vision to identify specific parts of an image to make sure that somebody who is maybe blind or deaf, they can understand the environment around them and they can live in a safe world. Now, we're going to look at how computers can actually see, because as we've learned in previous lectures, computers don't understand direct input and they only work in numbers. So to understand an image, all it is a two-dimensional representation where each location in that two-dimensional representation contains a value for color. For example, let's say we have this grayscale image of Abraham Lincoln, which is at a very low definition, and we can take it to a numerical format by giving each pixel a value from 0 for black and 255 to white. This allows us to numerically represent our image, and the computer will not see any actual colors. It will simply see the matrix of numbers. For example, if you want to have more colors than just this grayscale, we could use RGB, or red, green, and blue, to represent 3 different colors for a rainbow of colors, and you would add a third dimension as each pixel now needs 3 values rather than 1. To use this pixel representation in numerical representations, we can use different tasks. For example, regression, where we could have a continuous representation of what the image may be, or classification, where we calculate the probabilities of the image being a specific label. Let's say we have our image of Abraham Lincoln in grayscale, and we pass it through our pixel representation through a neural network to get a classification for 4 different presidents, let's say, and our model predicts that it could be Lincoln, most likely, but also Washington, Jefferson, and Obama have some probabilities as they are represented in our label distribution. And overall, that is how convolutional neural networks work. For different types of images, we have different types of feature detections. In human faces, we can work with a nose, eyes, and mouth. In cars, we can work with the wheels, the license plate, the headlights, the doors, and in a house, we could identify the windows, the steps, the doors, the bushes, the grass, and this allows us to see if an image can be classified and what it should be classified as using our deep learning methods. So, for manual feature extraction, which we would perform normally to detect specific features, we would take a given knowledge that we have, we would define the features based on that knowledge, and then we would use a neural network with those features to detect if an image is a specific classification. However, this has many problems as images are very diverse data. There could be different viewpoints or different angles that the image is taken. There could be different lighting conditions that our image is at, scale of the image as well as the objects inside of the image, deformation, where an object may still be classified in one way, but our neural network does not understand that it is that object, background clutter, where different textures are represented as similar although they are different objects, occlusion, where there is a very stark contrast between different colors, and intra-class variation. Intra-class variation is actually the most important, as we want to make sure our neural network will be able to distinguish between different classes or labels while it can still identify specific variations inside of each class. For example, in chairs, there are many different types of chairs, and we want to make sure our model understands what a chair is while also not confusing it with other non-chair items. So we can see that the main problem here is defining the features and having the detecting of those features for classification. And that is where the convolutional neural network architecture as well as other architectures come in. This allows us to learn different features from an image, starting at a low level, going to a high level, instead of manually defining them. So we start with our low level features, such as different edges or dark spots for a face. Then we get to our mid-level features, which could be eyes, ears, noses, and more of the smaller parts of a face that we see. And finally, we can get to the high-level features, like the facial structure and facial shape. And we can take this idea of learning our features so we can see how we actually learn them with a neural network. In the last lecture, we explored the fully connected neural network, which starts with an input and passes it through several different hidden layers with much more neurons, where every input goes to every different neuron until we eventually reach a final output for different tasks. And if we wanted to use this neural network architecture that is fully connected for our image tasks, we would theoretically take our 2D image, convert it to a one-dimensional representation as a vector, and pass all of those one-dimensional inputs at the same time. This would allow us to understand our image, but it would get rid of the critical spatial information where across different layers of the image in two-dimensional space, the representation across those 2 dimensions is lost, and the exponential factor of different image sizes can lead to many, many parameters, and the model will become very large and hard to work with. So we need to understand how we can use our spatial structure from our input with 2 dimensions so we can allow our network to understand it. So let's come up with an idea. We can use different patches from our input and pass them through neurons into our hidden layer. This is based off of our first fully connected architecture, but now works with our 2 dimensions. So each neuron will only see the specific patch that it works with. If we do this for all of the given patches in our image, we can receive a smaller 2-dimensional representation that has more information embedded while also maintaining our spatial structure. We remember from the last lecture that we need to take these neurons, and we need to perform a technique called backpropagation in order to improve our model's accuracy for the task that we are training it on. We do this by optimizing different values called the weights. So we need to understand how we can use weights on these patches. So let's define our new term called a filter, and let's say it is a size 4 by 4. This means for each filter we need 16 different weights. We can apply the exact same filter across our entire image, and that method of using a filter is called a convolution. We can use this convolution operation to apply different sets of weights or filters so we can understand features in an image. We can use multiple different filters to extract different features. Finally, we can share some weights across each filter in order to increase efficiency. Now want to use our convolution for an actual example so we can understand why it's important to retain our two-dimensional structure and use these different filters. So we are going to use the example of identifying different X shapes. We cannot compare different shapes directly because different X's can be written in different ways. For example, this perfect X that we have is completely straight with two crossing lines, whereas our X on the right has the opposite and some of the parts of the X are shifted. This means we cannot directly compare these two images, and there are much more other representations of our X that could confuse our model. So what we can do is use different features of X. Basically, at the deepest level, an X has a cross in the middle and different arms going in diagonal directions. If we can identify the specific parts of our X, such as the cross and those diagonals, in each image with our patches, we will be able to ensure that our model can understand different diverse X's. Now, based on this problem, we can define 3 different filters so we can have each part of the X. We can have 2 filters, each for the different diagonals, going from top to bottom and bottom to top, and we can have our third filter be the cross hatch in the middle of our X that has sort of a 5-die shape. So let's take these different filters with a convolution and pass our filter across the entire image. We can do this by looking at each 3x3 part of the image and multiplying it with our 3x3 matrix. If we multiply each part of our image with each item inside of our matrix for the convolution, we can get a new 3x3 matrix that tells us if each pixel matched or not, and we can sum all of those values to achieve a final value for each of our convolution operations. Let's take an example where we have this 5x5 image and we want to use a 3x3 filter which has our X crosshatch, and we can slide this filter across the input image. We can take our 3x3 filter across our 5x5 image, and we can element-wise multiply for each possible 3x3 part of our image. If we start at the top left corner and we matrix multiply, we can see that we get a value of 4 for the specific part of the image. And if we continue for each possible part of our image, we can now have a new 3x3 representation of our 5x5 image called a feature map. This summarizes the important information in our image and allows us to progressively create smaller and smaller feature maps to understand our image at a deeper level. Now, this idea of a feature map has been very well experimented with, and there are actually different feature maps we can use on images to perform different tasks. Let's say we have this image of a woman's face, and we want to perform different operations on it. To sharpen the edges in this image, we can use this specific 3x3 filter. We can see that the lines in our image are much sharper, and there is more of a contrast. Additionally, to detect different edges in our image, we can use this other 3x3 filter, which highlights the edges in our image in white and leaves the rest black. We can also use a strong edge detect, which highlights our edges in a more white color using a different filter. Note that there are many other different filters that we can use to produce feature maps, And depending on your task, you may not have to use any of these, and you could create your own depending on what you need for your task. So in summary, to perform our feature extraction using these convolutions, we are going to apply a set of weights, which is called the filter, across our entire image to extract the specific features progressively, and we're going to use several different filters in our image to extract different features we want to understand. Finally, we're going to ensure that for every filter we use, the different weights will be the same as long as our filter is supposed to be the same, so we can compress our image to a more dense information representation. Let's use this convolution operation to create a convolutional neural network, or CNN. RCNN is going to take an input image and perform many different convolutions on it to receive many different feature maps. Then we will perform an operation called max pooling, which simply just compresses our convolution to a more dense representation. And we will finally flatten this max pooling operation to make it one-dimensional and pass it through different fully connected layers like we did in the last lecture to achieve a different output. Additionally, in our convolutions, we are actually going to be using a nonlinearity, and this is often the rectified linear unit, or ReLU, due to its simplicity and ability to remove all negative values. For our convolution, we have different ways of representing this convolutional layer in code. In TensorFlow, it is called Conv2D, whereas in PyTorch, it is called Conv2D with a lowercase d at the end. For our nonlinearity, we can use many different activations, but in TensorFlow, this starts with tf.keras.activations, and you can choose any of them from different names in the TensorFlow documentation. And then similarly, in PyTorch, we can use torch.nn. Finally, for our pooling operation, which is max pooling in this case, we can use the max pool 2D layers from TensorFlow and PyTorch. What we're going to do for our convolutional neural network is we're going to train it using our image data to have our convolutions work with better data to have more accurate classifications, and we're going to learn different filters for those convolutions that will allow us to understand our input better. Again, with our convolutions, we will take our filter and we will summarize it to a specific weight inside of a more dense representation, and we will also apply a bias, which we originally did in our first and second lectures, to ensure that no weights are specifically given too much importance. And as an example in math for how we would represent this, each particular pixel inside of our given filter is going to have a weight by input multiplication and adding the bias. This is similar to what we did in recurrent neural networks from our last lecture, but now with 2 dimensions, we need to account for the different pixels in our 2 dimensions with different weights. Now, we also need to introduce this idea of depth, as we are going to have many different feature maps that we are going to learn. So we are essentially calculating an output volume where the height and weight are our spatial dimensions for our image, and the depth is the number of filters that we're going to be learning. Additionally, a term called stride represents how many pixels we are going to be moving between each part of our image for each filter. In code, with TensorFlow, we can define our convolutional layer by having the number of filters, the size of our filter, as well as the number of strides that we are going to take. And then PyTorch, we can do this similarly by also defining the number of inputs and number of outputs we're going to have. Additionally, we need to introduce some nonlinearity into our network, which we're going to apply after every convolution that we have, or after every convolutional layer. With our rectified linear unit, we simply only have all of our negative values set to 0 and all positive values unaffected. This is very important because in an image where you may have positive and negative values for different pixels, you can use our nonlinearity to only represent the non-negative values. This is a very simple operation that also introduces nonlinearity, which is very important for problems in deep learning, as data in the real world is often not actually linear and requires nonlinear representations. For our pooling operation, Essentially, what it does is takes a original input with a pooling size and the number of strides to take all of the values inside of a given pooling filter and finds the maximum value to achieve our reduced dimensionality. So in TensorFlow, what we would do is use the max pool 2D layer, defining the size of our pooling as well as the strides between each of our filters. And in PyTorch, we would do this similarly. So with our reduced dimensionality, as well as more spatially dense information, we can further downsample with multiple convolutions and pooling layers to achieve a more and more dense representation. So in summary, how we would use our low to high level features is for each convolutional neural network layer, we would learn different features starting from our lowest level to our highest level. So in our layer 1, for facial detection, we would start with our edges. In layer 2, we would get to our middle level features with a larger representation. And in our final convolutional layer, we will look at the highest level features like face shape. Let's look at a longer representation of our convolutional neural network where we take our input image, we pass it through a convolution with a nonlinear activation, and then a pooling operation. Then we do the same with a convolution and pooling layer again, and this has our convolution operation, which we talked about previously. It has our nonlinearity, which is most often the rectified linear unit, and finally, it has our reduced dimensionality with pooling to achieve more dense information. Then, after all of our convolutions have finished, we flatten this 2D representation to one dimension, pass it through several fully connected layers to eventually get a representation called a softmax, where each respective label that we may have is provided with a given probability value. This allows us to perform our classification task with different probabilities for each of our given classes we want to classify. In code, let's look at how we could create a convolutional neural network with the sequential API using TensorFlow. We start with our first convolutional layer, where the conv2D is used with 32 filters, a filter size of 3 by 3, and an activation function of rectified linear unit. Then our max pool layer has a pool size of 2 by 2, which is our pooling filter, as well as a stride value of 2 to move 2 between each filter. We do this similarly in our second convolution, where we now actually have 64 features that are learned to have a more dense representation of information. And after the second max pooling operation, we flatten this two-dimensional representation, put it through several dense layers to eventually achieve our softmax output of probabilities. We can do this similarly in PyTorch with our convolutional layer defining the number of inputs and number of outputs, as well as the size of our filter, introducing a nonlinearity, and using a max pool operation. Then we do the same in our second layer, now with 64 convolutional filters, and then we can use our flatten layer to pass it through several different dense layers to eventually get our final probability output. Now, the convolutional neural network architecture has been used for classification so far, which we've been inspecting, but there are many other applications we can use. When we saw with our last part where we flattened and performed several operations to achieve our softmax with probabilities, if we replace that, we can perform many different tasks, such as object detection, segmentation, and probabilistic control, where we look at different probabilities of specific objects inside of our image. As an example for classification, which we've been looking at, in breast cancer, there's actually a paper on Nature Journals, which is a highly respected journal. We can see that AI was actually able to have better breast cancer detection than professional doctors, where the case was sometimes missed by the doctor but detected by AI. In object detection, we can take an image and give it a label, as well as identify where it specifically is in the image. Let's take our image from the start of the lecture, where we had a taxi, and we can identify that it is actually a taxi with our convolutional neural network, as well as identify specifically where it is with a box to understand the specific spatial information. And in object detection, we actually have several different methods of performing this. So if we want to have multiple objects detected, we can simply train our convolutional neural network to have several different objects available. If we look at our taxi image from a different angle, we can see 3 new persons as well as a truck off to the side. A simple and naive way to solve this problem would be to look at every single possible box in a given image and classify it to see if there is anything there. However, this introduces the problem that there are extremely way too many inputs, and with every new pixel that you introduce to our image, the number of boxes we could possibly have exponentially increases, as we have to try every possible width, every possible height, and every possible location. A better way to do this would be to use the RCNN architecture, where we have different regions in the image that are proposed. So the way this works is that we have a model that we use to extract specific parts of the image that look like they possibly have something in them, and then putting each image through our convolutional neural network to classify it. This allows us to have less of our boxes than we had before, but this is still slow, as there are still many different regions, about 2,000 usually, and these region proposals that we have, where there may be something, are often manually defined and can be extremely brittle in practice, where sometimes new images can break all of the regions that you may have. We can solve this by using the fully convolutional neural network architecture, where rather than flattening at the end, we simply deconvolute or reverse the convolution operation by first starting with convolutions and then doing the opposite to achieve a new prediction output. Let's say we have this image of cows in a forest, which is in RGB. We can pass it through our fully convolutional neural network to accurately see where the cows are, where the trees are, where the sky is, where the grass is, as well as other parts of our image. Note that in code, to perform this deconvolution operation, use the Conv 2D transpose layer, or in PyTorch, the Conv transpose 2D. This is called transposition, as transposition is often used to reverse an operation. Now, this can be actually applied with navigating through autonomous cars, where you can provide an input of a perception from the camera in the front of the car, as well as different GPS maps on the roads to provide the model with a representation of where the car is and its environment, as well as the different options it can take to drive safely. This allows us to output different steering wheel commands, where we can turn left or turn right or keep going straight depending on the situation. This would work by first interpreting the entire environment, perhaps by 3 different representations from the front of the car, the right of the car, and the left of the car, as well as the maps. We pass each of these images through a convolutional layer and then flatten it like we did for our classification, and we combine all of these flattened representations together to continue with our model. We can then use several fully convolutional layers, which we introduced, as well as the routed map through a convolutional layer again to achieve different examples. So if we want to have a control output where we have how much we want to steer, that can be used with more fully convolutional layers, as well as several different values, which create a representation of how much the steering wheel should turn left or turn right. However, if we want to have a control of one singular direction that we want to turn and where we should specifically turn, and we inputted a map where we have our route, this could be done by taking that route, putting it through a convolutional layer, flattening it, and adding it to our fully convolutional inputs, so that way the car can understand which direction it should turn to drive safely. And computer vision with the convolutional neural network architecture, as well as others, is extremely important. We saw how it can be used for classification or in autonomous driving, but there are much more examples like image generation, robotics, medicine, and so much more. So it is extremely important to understand these concepts so you can help solve real-world problems that can benefit from deep learning. In summary, we covered the foundations of computer vision as well as how computers understand how images are represented through different numerical representations. Then we looked at the convolution operation so we could extract different features from an image. We used that convolution operation to create convolutional neural networks, and we saw how the architecture of that convolutional neural network works and applied it to the classification problem. Then, with our applications, we saw how we can sometimes have different parts of our image represented. We could have our image captioned, and there are many real-world examples where there are applications in facial detection for security, in cancers for medicine, and robotics for allowing robots to understand the world around them.